Welcome to episode 2. We are going to be launching 3 bottle rockets. We have changed the big one and it is much taller.
What else does it have?
We have put some electronics in it. We have also added some parachutes.
Do you think the parachutes are going to work?
I'm not sure about the parachutes, but I know how we're going to launch this.
Okay. What are the other rockets?
The other rockets are just small ones. They're normal. We haven't changed much from last time.
Okay. Have we changed the launcher?
Yes.
Can you show us that? Alright.
So when you're pumping, so the pump goes in there. When you're pumping and when you're finished, I'm going to pull this down.
Yeah.
And hopefully it will launch that way.
It
like
will.
Not into the field.
I'm a bit worried that we've put the tent up to keep the sun off us, but actually the wind is blowing the opposite way today, isn't it?
Yeah. Which way? That way. That way.
It's going to blow towards the tent, isn't it? So it might move the tent. We've also got another camera with us today to try and get some better video footage. Alright.
Yeah.
Happy?
Yeah. We'll be doing this for that. We're going to have 6 launches because we've got 2 bottles of water
We've got
this time. We are filling up the rocket. We are attaching the nozzle to the bottom. We are adjusting cameras before the launch. This is the small rocket that is light. Flight 1. I launched it. Dad went and it went into the air like a firework. It got damaged slightly on the nose. Flight 2. The camera did not get the whole flight. Flight 3. I filmed this. This is the big rocket, and the top got pushed in when it fell. The parachutes did not launch, and it twisted over fast in flight. My sister helps, but it is not strong enough without help. This is the medium rocket, and it went up then and had a few dips and dives. Launch 5 was fast but sideways. Flight 6 went really far and quite high. Flight 7, Mummy launched. This went quite high but sideways.
So a couple of things worth looking at on this one is that first of all, every single one of the launches shot up and went sideways, mainly probably due to our new nozzle. What we'll do before the next launch is rebuild that nozzle so it sits in the same launcher. We also found the launcher wasn't very stable when we put the larger weight rockets on it. So ignoring the fact that all the rockets went sideways, what I want to do is actually do some looking at a couple of the flights in particular where we've captured it from the side so we can begin to measure the speed of the launch. To do that, what we did was we took each frame of the video out, we stuck them in Photoshop. Photoshop has this cool way of laying all your different frames so they overlap nicely. It's part of their landscape layout sort of tooling, so you can basically overlay these perfectly every single time. We then layer masked each one and lay them out. From that we can make this quite nice looking picture which has every single step of the rocket on. And then we can measure the distance on the picture between the nose point of each one or the back fin of each one. That gives us a distance in pixels between each point. If we measure the rocket and we measure the rocket in real life, we can come up with a ratio and actually work out how far the rocket travelled between each frame in a 30th of a second, because that's how many frames per second our cameras were taking. Now, the outcome of that is quite interesting. We immediately see that there was a very sudden speed at the start, which you kind of expect because the water pressure is reflected off the launcher. You expect that very sudden burst of acceleration, the very high pressure in there. And then what happens next was a bit unknown, and perhaps we should really think about why it was. There's a couple of anomalous readings in the middle. I was kind of expecting it to be a slow launch and a faster later, because at the beginning it's got a lot more water in, and then later it hasn't. However, at the beginning it's also got a lot more pressure in, whereas later some of that, the volume of air has doubled, so the pressure would have halved. So even though there's less mass, it's pushing out the water slower as it is later. What we actually see in the graph is a very straight line. So with these anomalous readings in the middle, I thought, well, maybe this is just a scientific error. Maybe it's that the frames weren't quite accurately spaced out because the video had been transcoded slightly. And if you sort of ignore them slightly or average those 3 frames out, you do get a very straight line. However, I thought, I've got more than one rocket video here. Let's look at a second one. So we did the same thing a second time. So on the graphs ahead in front of you, see first of all that we did flight 4. Then what I did was I analysed flight 7, and because I was a bit surprised by the results of that, I thought, well, I still have another flight I could do with flight 5. Flight 4, it was a flight which flew at 90 degrees to the camera, so we got quite good data. Flight 7, however, flew away from the camera, so as it began to turn, we couldn't really take accurate measurements because the measurements would look shorter and shorter and shorter, but it's really because of the fact it's going away rather than the fact it's decelerating as such. First of all, the speed. Now, this is the speed graph of flight 4. It's very consistent. You see here's the couple of weirdnesses, but it's kind of this sudden sharp straight line up to here that it tails off here because we're run out of water. If we look at the same graph for flight 7 for the first few steps, again, very sharp sudden acceleration, and then weirdly here we have this anomaly here again where it's not quite linear. And what's interesting was, I thought, well, if I overlap these two graphs, what would I see? Before I go to that combined graph, we did flight 5 as well. Flight 5 had a few more steps before it went too far off angle. Looking at this combined graph here of the different flights, you can see that they're actually surprisingly well put together. Like the experimental error here, what's interesting is the flight 5 here is much sharper, and that's probably due to not launching exactly on a frame as such. There is some error here. If you made flight 5 one frame later in all its recordings, it would be under the other flights, but still quite in line with it. The acceleration graphs, I should mention very briefly, these aren't actually accelerations in meters per second or anything like that. They're actually the delta between the 2 frames. So it's the instance, it's the speed change between those 2 frames. So really it's in, I guess, meters per 30th or millimeters per 30th of a second is really what this axis here is. And you can see it's not really consistent. It's always positive until the end, but there were some negative ones here because the speed change did change between those 2 elements. So looking at the combined distance, which is the summation of each one of those, we see the graphs here are almost too close together to analyze. What I did then was I truncated the graph, so I didn't have I didn't have these high points sort of blowing the scale out. So when you truncate the graphs together, you can see how close these points actually are to each other. I haven't calculated a percentage here, but I would say this is well within experimental error here. And there are differences. We weren't perfect on the launch times, we weren't perfect on the pressure, we weren't perfect on the amount of water in each one. So it's quite interesting to see how close these data points are to each other, well within a good scientific level, at the sort of levels that we're working with right now. And again, for distance travelled in meters over the first quarter of a second, this graph here is just showing how tight these points together are. So for next time, I think what we're going to do is start looking a bit more accurately at the pressure and the water levels and trying to fix the water level and fix the pressure. Fixing the pressure is quite easy because we've got a pressure gauge. Fixing the water level is actually much more trickier because when you attach it to the hose pipe, first we have to attach it without losing any water, but also some water goes back into the launch tube, so we have to probably empty the launch tube and fill it without dropping any. So we have to be a bit careful about how we attach that together. So I think for the moment what we can see is that we are getting quite good scientific data out of this, but we have to basically rebuild this now with more controlled variable. So thank you very much for watching. We'll be back next time with a bit more more accurate data as to what we're actually flying, and maybe using some of the small rockets. The small rockets were a lot more fun to fly. They were a lot more reliable to launch. They were easier to get up to the pressure because they had a much smaller volume to pressurize. So what we'll probably do next time is rebuild the nozzle, rebuild the small rockets because they kind of disintegrated with the water, and give you some more accurate scientific measurements. Thank you very much.